560, right? So example 20 hills. The cart's up here at the top. I know I had a better picture yesterday. It's 41.1 meters tall. The cart weighs 2,000 kilograms. So to find the total energy, right, mechanical energy, we need to add the KE and the PE, right? Right? That car is not moving, so what do you, right? So the only mechanical energy we have up here is PE, which equals M times 41.1, and what does that equal? 805,560 joules. Does that make sense? It goes down the hill and we get down here at the bottom, right? What happens to all that potential energy? Good, with the yawn and everything, it must be that boring. All this potential energy turns into kinetic energy, right? Because down here at the bottom of the hill, we're assuming the height is 0. So that means our mechanical energy is still KE plus PE, but the PE is 0. Does that make sense, guys? Yeah? What do you know about these two mechanical energies? They're the same because our mechanical energy initial equals our mechanical energy final, right? So the total energy down here is 85560 joules, and that equals the kinetic energy. Does that make sense? So mechanical equals the sum of these two, that's 0, so that means all we have at the bottom is kinetic. Does that make sense, guys? Yeah? Okay. Oh, we're not done with part B yet. We'll get there. No, we can't talk about the sequel before we're done with the movie.
Well, you were talking about it yesterday.
Okay, so okay, guys, thank you. All right, so now how do I find this velocity? Okay, 1/2 times 2,000 is 1,000, right? So I divide this by 1,000, right? Divide that by 1,000, 1, 2, 3. So 805.56 equals V squared. What do we do now? Square root.
So it doesn't know.
What?
So it doesn't know.
What'd you say?
It doesn't know.
It doesn't what? I don't know what you're saying. Okay. So, square root the 805.56, and what's our velocity? 28.4. Does that make sense? No, why not? Okay. All right. Any questions, guys? Guys, any questions? All right, C. The second hill is only 25 meters tall. What's the total energy of the train, and what's the train's velocity at the top of the hill? Well, we know that energy is conserved, right? So when the train gets back up here to the top of the second hill, which is 25 meters tall, what's the total energy there? Really, Richard? Energy is conserved, right? So how much did we have to start?
It's the same amount.
We had this much to start, right? We had this much down here, right? Right? So how much do we still have right there? The same. Good. So our mechanical energy equals 805,560 because energy is conserved. And there's no outside forces acting. There's no friction acting. Okay? Yes, Michael?
When will the mechanical energy not be the same?
When there's an outside force acting.
Outside force?
When there's friction.
Oh.
When there's someone down here at the bottom pushing the car along a little harder.
But when it's just still like that.
Yep. When we're ignoring friction, which is what we're doing, energy is conserved. Okay? Now, when the cart started down here, the only force acting on was gravity, right?
Right.
When the motor pulled the cart up to the top, an outside force acted. Okay? So from here to here, that's not part of our system. Energy is not conserved. Energy is added to the system because the motor lifts it up. Does that make sense?
Yes.
Once the motor stops lifting, that motor is the outside force. Once that motor stops lifting and the cart's sitting at the top, almost motionless, all it has is potential. That's all the energy it has. It keeps that energy the whole way through as long as there's no friction. Not exactly real life because there's air resistance, right? And the track makes noise and other things. But it gives us a good stepping stone to talk about when there is friction involved. Okay? So how can I find the velocity here? Well, does the cart have potential energy here? Yes. Does it have kinetic energy here? Yeah. Okay. It will have kinetic energy here because it's not to its highest velocity yet, right? Or highest height yet. All the energy isn't turned back into potential. If all the energy was turned back into potential, the cart would be up at 41.1 meters, right? So this means only some of the energy is potential and some of it is still kinetic. So that means I need to take these two. I need to keep KE and PE both, right? Right? What's our mass still? 2,000, right? What's the height here? 25. We want to find the velocity. So we know 1/2 mv squared plus mgh equals that 805,560 number. It's a big number, right? So now we can plug things in, can't we? Right? What goes in for our m? 2,000. V squared, we don't know v, plus 2,000 times 9.8. What's the height? Right? You got your calculator, right, Julian? All right. Where's your calculator? Somewhere. Okay. Out grazing in the field by itself somewhere. Probably hanging out in the hood. All right. So 2,000 times 9.8 times 25. What does that equal? Enough. Thank you, Richard. You are extremely helpful.
I think he should be inaugurated as a peanut gallery member.
Yeah. He's in his own gallery. Okay. So now what I do? Subtract, right? So now a really complex kind of very involved situation turns into a kind of simple algebra problem. You guys are probably loving these algebra problems compared to the ones we did last chapter.
Yeah.
So 315,560 equals 1,000 v squared, right?
Yes.
Divided by 1,000. Right? 315.56 equals v squared. Square root. What do we get, Moses? 17.8. And you guys probably all remember this from riding roller coasters. If you haven't ridden one yet, we can ride one on May 17th, provided that you are passing. All right. As you go over smaller hills, what happens to your speed? Progressively gets less. But as you return back to that lowest height, what happens to your speed? It goes back up, right? Because when we're at low heights, then all of our energy is turned into, or most of our energy is turned into kinetic, so our velocity goes up, right? Because down here's our highest kinetic energy, highest velocity. As we go back up, some of our kinetic turns back into potential, giving us the height, but takes away from our kinetic energy. So it makes our velocity less. And if we ever reach the height of 41.1 meters again, what would happen to our car?
Stop.
It would come to a stop again. Okay? Assuming energy is conserved. But in real life, energy is not conserved. Otherwise, what you would do is you'd have the boarding for the roller coaster to be up here at the start. It'd go up here at the top of the hill. It'd go around a big track and end it back up at that starting gate. But energy is not 100% conserved because of friction. So this is an idealized situation. Does that make sense, guys? Does this make sense? Yeah? Okay. Let's try another one like this. Is saying, yay! More, oh, I don't want to do that. More energy conservation. Where'd you go? There you go. All right. So 21 down here. A 40 kilogram child is sitting atop a 4 meter tall slide. What's the total energy of the child at the top of the slide? What's the child's velocity at the bottom of the slide? What was the child's velocity when they were 2 meters above the ground? Okay. So, let me draw a picture. I find that these problems go a lot easier when I draw pictures. And this is why physics is not for doodlers, because usually doodlers get confused and distracted when they start drawing pictures, which is why Mr. Branch really has to focus. They're scared. Slide is 4 meters tall. Does it matter what the slide looks like?
Yes.
If it has 2 bumps or 1 bump or kind of this little like U shape, does it matter?
Yes. It doesn't, but I want to say it matters.
No, because it's still displacement is still 4 meters, right? Work done is path independent. So it doesn't matter how the slide looks.
Well, if there's bumps,
Okay.
they fly off it.
Well, they might.
So like it can have a loop, right? And as long as it doesn't matter because of the sport.
Happy at the bottom of the slide. Okay. Then we want to find the velocity here as well. That's 2 meters above the ground. So there's our picture. What am I doing? What am I doing? There we go. Okay. Oh, how big's the kid? 40 kilograms. All right. So mass equals 40 kilograms. So when we're up here at the top, what type of energy do we have? Potential, right? So do we have any kinetic yet? No, because they're not moving yet, right? They're just hanging out. So at the top, we know that PE equals mgh. What's m? 40. What's g? 9.8. What's h? 4. So 40 times 9.8 times 4. What does that equal? 1,500 and what?
68.
68. Hey, it's a good number to the end. That's my football number. Just a 68. 1,560. That'd be a big number. All right. Any questions? Any questions? Part B. They want to know what type of energy or what our velocity is at the bottom, right? Right, Amina? Does the kid have any more height at the bottom? No. So that means all this potential is turned into kinetic. We're at maximum potential. We're at maximum kinetic right now, right?
Yes.
Okay, so if we look at it from this idea, ME initial equals ME final. We know our kinetic initial plus PE initial equals kinetic final plus PE final, right, guys?
Yeah.
Right? Does that make sense?
Yes.
Yeah. So before we get started, what type of energy do we have?
Where?
Or when we get started, what type of energy do we have? PE. So this KE is 0, right? Right? What type do we have at the end? KE. So because we're all right to 0, that PE is 0, right? Right?
In the middle is half mass.
So we have 1,568 because that's our potential energy initial, right? Right, guys? Equals 1/2 mv squared. Oh, v is, or m is what? 40. So we can solve that for v.
Right.
Yes.
Is it half and half right there? 2 meters?
What?
Velocity right there.
Is it half that 2 meter mark? We'll get to 2 meter mark in a second, okay? Okay. So can you guys find the velocity?
More or less.
Okay, find the velocity real quick.
That's
1568 divided by 20. Well, it's 156.8 divided by 2. So that's going to be like 75 plus 3.4, so 78.4. And square root that.
8.85.
8.85? Okay.
Ooh,
So we divide by 20, right? And we get 78.4 equals v squared. Then we square root. What did you get, Gulnas?
8.85.
8.85. Good. Does that make sense? Any questions about that? Any questions? All right. For part C, they wanted the velocity at 2 meters, right? Right? Will be more or less than 8.85. Will be more or less. Will the velocity at 2 be more or less than 8.85? Less. Why? Good. We have less kinetic, right? Here we have some potential and some kinetic, don't we? So ME initial equals, I guess we really can't call it final, but it's just the convention because it's in the middle. Could call it ME middle if you want to. Alright? But we know our total energy to start equals our energy here in the middle, right? And we have both potential and kinetic. So we have kinetic energy right there, right? Or potential, either one. Okay. Some of you get the joke, some of you don't. Okay. So we need to do mgh plus 1/2 mv squared. Right? Mass is still 40. We're still on the Earth. Height is still 2. Mass is still 40. And you need to solve for V, right? Can you guys take a few moments and solve that for V for me?
I suppose.
6.3.
Take a few moments, not one moment. Check and see if Gunas is right. If you didn't hear it, good. Thank you, Gunas. Yeah. 0.56. You divide it by 100, it's 1,000.
Oh.
Okay.
Without result.
Okay. Otherwise, your work is right. You just divide by the wrong number.
I got
What'd you get?
6.3.
So Gunas is right?
Okay, I got it.
Okay. So, Michael, we do 40 times 9.8 times 2, right? Subtract that from this.
Okay.
Then divide by 20 because half 40 is 20. And that's how you get your final velocity of 6 point. Yep, oh yeah, square root again, thank you. Okay. Do not forget to square root. If you get 36 point something, that means you didn't square root. Or 39 point something. Okay. Do these make sense, guys? Yeah. Are there any questions? Any questions? What's your question, Sergio?